problem that we did Wednesday of week 7. And we were talking about Ampere's law. And Ampere's law says that the total sum of the magnetic field around a closed loop, so the L means a path, and the circle on this integral means that it is a closed path, so a closed loop, is equal to mu naught times the current that goes through the lasso. So the current that goes through the lasso of your loop. So the first example we did of this is just finding the current due to one wire. And just as an aside, you should remember that when we did problems like this with the electric charge, we could have to find some little bit of field here, little length of the wire, and we'd have some current I, and maybe at some point out here, we would have to then find the dot product that goes to this point, and then we would have maybe magnetic field and get only the component, and so on and so on and so on, and then we could integrate, but Ampere's law saves us from having to do all of that. And so instead what we do is if you have a wire with some current, and I want to know at some distance out here, some distance, say, h away from the wire, I'm going to make an Amperian loop that goes around that wire so that my wire pokes right through it. So this is kind of a side view. And the top view looks like this. You have the wire coming out of the page, and if I want to know the magnetic field, say out here, which is what we're all about here, finding the magnetic field, then I would make an Amperian loop that goes through that point all the way around the current that's causing that magnetic field. And so then we can see then that the integral, and again, this is one of those integrals that isn't really an integral, because now the magnetic field, so I'm putting my thumb pointing out of the page, and so here's my thumb pointing this way, and my fingers, it's supposed to be my fingers, are pointing this way, so I know that the magnetic field points up, and so it is along the loop the whole way. And so this is the magnetic field times the whole path, which is the circumference, 2 pi, what did I call it, h of the circle, and that equals just my current that's going through it times mu naught. And so I get that the magnetic field due to an infinite wire is mu naught over 2 pi h times I. And that's the answer. So a lot easier than trying to integrate the Biot-Savart law. So part B then said, what about a whole bunch of coils? And again, we could do this problem, right, where we could write one coil and then we could figure out the field over here and, figure out this piece, right? And then we could, add a bunch of coils and we could integrate again, but we're not going to do that. Instead, what we're going to do is we're going to take this coil, and I'm actually going to do a slice view. And so what you want to imagine here is that you have this is like a hot dog bun. So you have this round hot dog bun thing, and I'm going to slice the hot dog bun. And so what I'm left with is just the wires poking out here. This is like the crust of the bun, okay? And so here's all the current coming out. This is a coil of wire, and then here's all the other wires going in, like this, okay? And so this is the same current going round and around and around in a loop, so a loop of wire like this. This is called a solenoid. Okay, so now we're going to apply Ampere's law, and I just want to make a comment about this. Let's say, for the sake of argument, that I chose an Amperian loop that looked like this, that went across the whole thing. If this is my Amperian loop, and you imagine that the solenoid here goes through this, is that the I through is equal to 0, because for every current that's coming out, there's a current that's going back in. So this should tell you therefore that the magnetic field outside of the loop actually has to be 0, and the magnetic field outside of the loop has to be 0. Outside of the Ampere, at the top and bottom of the Amperian loop, and therefore inside and outside of the solenoid. So the purpose of the solenoid is to make a uniform magnetic field inside and no field outside. Now, real solenoids, of course, are not perfectly long, so there's a little bit of field outside, and then at the ends of the solenoid, there's fringing and stuff like that, but we're not going to worry about that. Okay, back to the story at hand. So, I made my diagram too messy. So, here's my current again, coming through all these loops of wires that I select like a hot dog bun. And this time now, I'm going to make a loop that looks like this. And so what I realize is that, again, if I put my thumb coming out of the board, so here's my thumb, I guess, and then what do my fingers look like? Here's my fingers. I need a video camera here. So this is like my fingers, right? And so I know that down here, the B field points that way. So along the loop, the magnetic field points this way. But that means that when I do the sum of B dot dl, that means that the dot product of the magnetic field and the path on the sides goes to 0. So the only part of this, and there's no B field outside, so actually the only part that survives is B times some, I don't know, what should I call it, L, length of my rectangle, my Amperian loop. So what's inside there? Well, what's inside is a certain number of coils. And so usually what you're given about a solenoid, though, is that it is n turns of the coil per length. And so if you're given that n turns per length, it's the little n times the length of your thing. That's basically how it goes, times mu naught. And so we find that B, due to a solenoid, is pretty much the easiest thing that you can get here is, oh, whoops, I forgot my current. So it's n times the length. That's how many turns there are, but I need to know each one of these currents coming out. So, of course, I have to shoehorn in here the current. Okay, there we go. And the thing I invoked, the L, fortunately that goes away, as I knew that it needed to, and I get N mu naught I. Pretty much the simplest thing we can do in this class for magnetic field. So, uniform field. Doesn't depend on how far away you are or anything like that, and it just depends on the number of turns per unit length and the current. Okay.